In today's tutorial, we will evaluate various ways for the synthesis of this dibenzyl ketone starting from toluene. Well, certainly the benzyl moiety completely derives from toluene, so we need to get a reaction in benzylic position. We have the possibility, of course, to transfer the methyl group into a nucleophile just by deprotonating. This seems to be a very easy, straightforward approach. Well, how can we deprotonate there? We need a strong base. Let's take LDA. If LDA, lithium diisopropyl amide, is not sufficient, then we can add some potassium T-butoxide additionally, and that combination is the so-called Schlosser superbase. This will certainly deprotonate here, and we then have this nucleophile, for instance, with a lithium countercation. So, what could be an appropriate electrophile? Well, we need the carbonyl group with two leaving groups. Let's take the chloride and it will react. We need 0.5 equivalents to that one to form then our target molecule. However, first of all, LDA is not cheap, and this one, phosgene, is, as you know, very, very dangerous. You don't want to work with that in your lab. Yeah. Well, let's change, for instance, those chlorides against alkoxy groups. Then we have the diester of carbonic acid. But as soon as the first one has reacted, then we have an ester. The second equivalent will react, then we have the ketone. Yes, that works. But that ketone is more reactive against the nucleophile than the esters have been in the steps before. So we can't prevent that preferentially the third equivalent will react and forming essentially a tertiary alcoholate. So this wouldn't work then. Let's have a look at an alternative. Not using this as a nucleophilic center, but as an electrophilic center. We can halogenate here in benzylic position, for instance, forming that benzyl chloride, a radical starter like AIBN, then SOCl2 for the radical chain reaction. Then we are here. Next step is substituting with a cyanide. So cyanide, then we have that nitrile. We can transform that nitrile into a carboxylic acid by hydrolyzing it, acidic conditions, water, or we need some more energy, heating it up. Then in the next step, forming the ester, and then we are here. So you might now ask, how does that help us getting from here to there? Well, remember the ester condensation, a reaction that works very well. What do we have to do? So simply using a base, sodium ethanolate, in ethanol, then in alpha position, the ester will be deprotonated. We will then have an ester enolate, strong nucleophile here. It will attack the next ester an addition elimination process resulting in this structure having a remaining ester group here. So, and this is a beta ketoester, and you certainly remember, if we hydrolyze that under acidic conditions, ethanol is eliminated, and then we have the beta keto carboxylic acid, and this is then sensitive in heating it up, and it will eliminate simply CO2, and we are at our target molecule. Thanks for listening.